Yeah, good morning. So today we are going to do basically uh, rather three winding transformer. But in fact, we can directly look at a multi-winding transformer or a n-winding transformer. So this is what we are going to do. N equal to 2, we have already seen that case. Now we'll extend it to a transformer which has many windings on its core. One, two, three. Three winding is very common, so that's what is really my focus of interest. But I'll start with the n winding transformer. So here in the figure, I have shown you a single phase n winding transformer. So cross section of that laminated core is shown here, and on this is the winding one, winding two, and the last winding, and in between are the other intermediate windings, the n windings put all together. Now look at it, I have also marked the dots of the polarities of it, and the windings are similar, exactly identically wound. So the dots also appear in the exactly identical locations, but the currents that I have shown, I1 is entering current and I2 and so on up to IN are all coming out currents. So the idea here is that, for example, one winding is connected to the source or generator, and the other windings, for example, are connected to the load. So therefore, by convention, they will be drawing power. So for such a three winding or n winding transformer, we can prove the following. Number one, V1 ratio of V1 is to V2 is up to Vn. The phasors will be same as N1 is to N2, the number of turns, N1, N2, and so on up to Nn. So uh, this is very straightforward. For example, if you look at V1 by V2, it will be N1 by N2. If you look V1 by V3, it will be N1 by N3, and so on. V1 by Vn will be N1 by Nn, where these are the number of turns on each of these windings. So therefore, put it together, Y1 is to V2 is to Vn. The ratios of them will be in proportion to N1 is to N2 and so on in proportion to N is to N. So very straightforward proof. Now let's look at the second requirement. The second requirement is basically the MMF balance equation. So what we are saying here is the that this is the magnetizing MMF on the left hand side, which is coming from the source, and on the right hand side is the sum of demagnetizing MMF. So N2I2 is the demagnetizing MMF in the second winding, and so on up to NNIN is the demagnetizing MMF in the last winding. This follows from our sign convention that these windings are creating demagnetizing flux, while only the first winding is creating the magnetizing flux. So ideally, of course, this whole thing, the difference of the magnetizing and the demagnetizing flux should be equal to phi times of R, where phi is the RMS value of the flux in the core and R is the reluctance. But because we are taking an ideal transformer for our discussion, so therefore R will be equal to 0, and once the reluctance is, because mu R is infinity, so the reluctance becomes 0, and therefore follows the second equation. Now comes the third equation. So we need to show the third equation, and for that let us start from the this equation itself and divide the above equation, MMF balance equation, by N1. So you will get I2 and so on up to Nn by N1 into In. But now you take the complex conjugate of this. So the N2 by N1 ratio being real, there is nothing to worry about. Similarly, Nn by Nn1 ratio being real, there is nothing to worry about. And so this becomes the complex conjugate. But now N2 by N1 can be written as V2 by V1 into I2 star and so on. This can be written as Vn by V1 into In star. Now take the I1 to the left hand side multiplying by, sorry, V1 to the left hand side multiplying by V1. You will get V1 I1 star is equal to V2 I2 star plus so on up to Vn In star. So that means P1 is equal to P2 plus P3 and so on up to Pn, and Q1 is equal to Q2 plus Q3 and so on equal to up to Qn. So therefore you have basically whatever is the input power in megawatts is being pushed out from the remaining n windings, which are the winding 2 to winding n. And similarly you have a Q balance equation, the P balance equation and the Q balance equation, which is to say that whatever is the MVAR which is pushed in from the winding 1 will be dispatched out from winding 2, 3 and so on up to winding n. Of course, if n is equal to 3, there will be only 2 terms, not in that case many terms. Okay. So this is a very simple concept. I mean, 3-winding transformer is just a generalization of the concept of 2-winding transformer, or rather a n-winding transformer, ideal transformer is a very simple generalization of the 2-winding transformer. 3-winding is very popular. For example, in a generating station, you will have a generator which will be generating a bulk sub. Yeah, I have an example here. So you will have a generator which is generating bulk power, which is in this case. So let's read it. A 3-winding 3-phase transformer feeds power from a 22 kV 3-phase generator to 400 kV grid. This is the transmission grid, and a local industry served at 132 kV. The 3-phase transformer is made up of 3 identical single-phase 3-winding transformer units in star-grounded, star-grounded, star-grounded configuration. Determine the required transformation ratios A1 and A2. Incidentally, this problem I have adapted it from Elgard, a book on electrical energy systems theory and introduction, a very beautiful book. So if you look at this example, so what we have got here is a 3-phase generator, and then this is grounded, so this is indicates this is a Y connection, and this 22 kV is a line to line voltage. Then it comes to a 3-phase 3-winding transformer. So each phase has 3 windings. One, this is the I1, and then this becomes the I2, and this becomes the I3 of the A phase. And similarly, not shown here but understood is the connection for the B and C phase. And we are just asked to the transformation ratios A from winding 1 to winding 2 and winding 1 to winding 3. So when we are looking at the transformation ratios, we should know what's the voltage which is being impressed across the winding. So the winding 1 here, it is grounded, right? A phase winding is is grounded. So the voltage which is going, this 22 kV is the line voltage. So 22 by root 3, that is 12.70 kV, will be the line to neutral or line to ground volt which will be impressed across it. Similarly, this is also a star connection. So 400 kV is again a line to line value. The rated values are typically line to line values. So you will get 400 by root 3, that is 230.95 kV. And the third one is also in the same configuration. So you will get 132 by root 3, that is 76.21 kV as the line to neutral voltage. Now A12 is nothing but equal to N1 by N2, which is nothing but equal to V1 by V2. So therefore, what do you say? What do? You take the ratio of 12.70 to 230.95 and it comes to this particular value. Similarly, A13 is nothing but N1 by N3, which is same as V1 by V3, and so that will come out to be 12.70 by 76.21, which is 0.166664, as this comes out the other ratio. So suppose I multiply this by 10 to the power 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So then it means that if I, what would that mean? If I take one turn on the V2, then I would need 5499 turns on the N1. And similarly, if I take one turn on the N3, then I would need 16664 turns on the N1 side. So, of course, it's better to, you cannot have two different turns on the N1 side. So, you should finally come back to N1 is to N2 is to N3 ratio and then convert it into appropriate integer value, but we'll not get into what should be the exact number of turns right now. Okay, now let's extend this problem a bit further. Consider the transformer in the figure 1. 600 megawatts and 150 MVAR are flowing out on the 400 kV line. So 400 kV transmission line is usually a three-phase transmission line which supplies power over a long distance, a couple of hundred of kilometers, for example. The local demand from the 132 kV bus, this won't be as is 99 megawatts. So obviously, because the voltage level is high, higher power is also being pushed out here. When we want to push out lower amount of power, then the voltage level is selected also for the HV side also has a comparatively lower voltage. And this 99 megawatts is at unity power factor. So find the currents and powers in all the three windings. So you know this, right? That V1 is equal to j omega N1 into the corresponding phasor phi. V2 will be j omega N2 into corresponding phasor phi. V3 is j omega N3 into corresponding phasor phi. So therefore, with respect to the phasor phi, V1, V2 and V3 all lead by 90 degrees. So they are on the same line as shown here, and they lead the phasor phi by 90 degrees. Now on the V3, V3 is the 132. This is V3, this is V2, this is V1. So on this is unity power factor load. On the V3 is a unity power factor load. So therefore, the current I3 is going to be in phase with V3 because of it being unity power factor. V2 being 400 kV side, I have shown it by the longest arrow. V3 being 132 kV, I have shown it by the next shorter one, and V1 being uh, 22 kV side, so I have shown it by the shortest arrow. But of course, this is not drawn to the scale. And now, just as I explained to you, that this power of unity power factor will be here at the I3, will be in phase with the V3, while for the V2, the current is the load is 600 megawatts and consider 6 are flowing out. So 600 megawatts and 150 MVAR are flowing out. So that means this is a lagging load. So because it's a lagging load, so the I2 current is going to lag the V2 phasor. And I have to calculate what is a, first thing I have to calculate is find the currents and power in all the three windings. So first is I should calculate I1. After I have calculated I1, I2 and I3 are known, then V1 I1 star, V2 I2 star, V3 I3 star. So let's start with the winding 2. I1 we will do it at the end because it is superposing the loads from the second winding and the third winding. So first we should understand what's happening with winding 2 and winding 3. So the apparent power, which is complex power, which is coming out of winding 2 is S2V2 star, and this is per phase value, right? You understand that whenever I write VI star, it is always a per phase value, but the load is actually 600 plus 150 megawatts, which is a 3-phase value. So I divide it by 3, and this is the megawatts and MVAR I get per phase. Similarly, 99 megawatts 99 megawatts plus J0 unity power factor is a 3-phase load on the winding 3, divided by 3, and you get 33 plus J0 as the megawatt and MVAR per phase for the winding 3. So now what should you do? You just take complex conjugate of this equation. So you will get V2 star I2 is equal to 200 minus J50, but then divide this whole thing by V2. But because V1, V2 and V3 are taken to be the reference phasors, I mean one is taken as a reference phasors and others automatically come on their line. So therefore there is no complex number operation here involved except for this side. So we take, to calculate I2, we take the complex conjugate of this, which will make it 200 minus J50 divided by the value of V2, which is anyway at the angle 0, So 2 divided by 230.95, and you will get it in rectangular coordinates, which you convert it into the polar form. The only thing just remember is unit here is kiloamperes. Why? Because this is megawatt and MVAR. So this is at the power of 10 to the power 6. This is kilovolts. So this comes in the power of 10 to the power 3. So when you have the scaling factor of 10 to the power 6 by 10 to the power 3, that is 10 to the power 3, which is kilo factor. So therefore the current becomes so many kiloamperes per phase. Similarly, 33 plus J0 is the power per phase on the third winding, and the phase to neutral voltage is 76.21 kV. So therefore your current comes out to be 0.433 unity power factor kiloamperes per phase. Now let's calculate I1. You should not make the mistake of directly applying parallelogram law of identity with respect to I2 and I3. Why? Because they are not on the same kV level. They are on the different transformer windings. So because they are on the different transformer windings, either everything should be referred to 1. That means you can do I3 dash. Suppose you refer everything to 1. So I3 dash is referred to 1. I2 dash is referred to winding 1. Then you do the summation, you will get I1 by superposition, by parallelogram law of identity. That is perfectly fine. But right now, we cannot directly apply parallelogram law of identity. Since I'll do the other way around, I'll not do the transformation. What I will say is that the three phase, this winding 1 supplies power to, complex power to winding 2 and winding 3. And we have already seen this relationship here. V1I1 star is equal to V2I2 star plus V3I3 star. So I am going to use that and say that V1I1 star is equal to V2I2 star, which is S2, plus V3I3 star, which is S3. So 200 plus J50 plus 333 plus J0, which is equal to 233 plus J50 megawatt and MVAR per phase. And therefore, now just divide it by the voltage V1, because when I take complex, first take complex conjugate, so this plus becomes minus. Since this is in line with the reference phasor angle 0, so there is nothing to worry, just substitute the real value there, whatever it is, 12.70, and you will get so many kiloamperes, as per phase, which is also the line current being star connection for this transformer. So find the currents and power in all the three windings. So we have calculated everything, multiplied by this by 3 to get the three phase value, and we have calculated all the currents and powers in the three phase winding. So such is a simple extension of a 2-winding transformer to a 3-winding or a n-winding transformer, single phase, and then subsequently the same thing can be used for 3-phase system. Thank you.